Hi everyone, Dr. Burns here, back with our discussion on integrated rate laws. So the rate laws that we talked about previously relate the rate to the concentration of the reactants. A second form of each rate law can also be written that relates concentration of the reactant and time. And this is called the integrated rate law. Integration in math typically means the sum of an area. However, what we're going to be talking about in terms of integration is over time. So instead of area, it's going to be the sum over time, which we have seen previously denoted as delta T. So we use integrated rate laws to determine the amount of reactant present after a certain period of time. So as our time is changing, we're going to see how much reactant is left over from that reaction. We can also use them to estimate the amount of time required for a reaction to proceed to a certain extent. Integrated rate laws are used to determine how much time is needed to store radioactive material so it can decay to a safe level. We will focus on first, second, and zero order reactions just for simplicity. We could do third order, half order, and negative orders, but those take a little bit more calculus base to them, which we're not going to do in general chemistry too. So let's look at first order integrated rate laws. So a first order reaction is a reaction whose rate depends on the concentration of only one of the reactants raised to the first power. So we know from our previous lessons that if it's first order, then we have just a 1 here. And if overall the reaction is first order, then there's only one reactant that is contributing to the rate or determining the rate of that reaction. We typically see this as having only one reactant in the reaction, as we see in our two examples here. In a first order reaction of the type A, the reactant that is contributing to the reaction order proceeds to products. We can express that rate as the rate of change in the reactant concentration using our rate expression. So here's where we're going to bring in our rate expressions and our rate laws. So we have a rate expression, but we can also write this reaction in terms of a rate law. But in these two mathematical equations, okay, we have rate is equal to negative delta A over delta T, and rate is equal to K times the concentration of A. But they're both equal to rate, meaning if they're both equal to the same rate for that same reaction, we can set them equal to each other. And that's how we're going to get a dependence on not only concentration, but also on the time. So we can set those two expressions equal to each other to get negative delta A over delta T is equal to K, the rate constant, times the concentration of A. Now, there's a little bit more calculus from that previous equation that gets us to our integrated rate law, which we're not going to do, so I've already done that for us. So using calculus, it is possible to show that that expression can relate to this equation right here. The natural log of A at some time t, so this is a later time, divided by the concentration of A at the initial time, so 0 means initial time, or time 0, is equal to the negative K which is the rate constant, times that time, that later time. Okay, so this t and that sub t are referring to the same time. So this is what's called the integrated rate law for first order reactions, which we can also refer to as a first order integrated rate law. We've done the integration, which is why we have t by itself now. Okay, the integration has been done, and that's where the natural log comes in. That's all of the calculus that's behind this, but we're just going to use it as an equation. Now we can rearrange this first order integrated rate law and get a new expression for it. We have natural log of a at some later time t equals the negative kt plus natural log of a at our initial time. And you'll notice that rearrangement in this way has the form of a linear equation. Y equals mx plus b, where k is m, our x-axis is our time, our y-axis is our concentration, and our b, our initial concentration, is where we are going to start, or where we cross that time axis. So slope is negative k, and our intercept is natural log of a at our initial time. So we can use both forms of this integrated rate law. Now we don't need to worry about finding that slope or anything like that. As I said previously, we are not going to focus on the graphical analysis behind rate laws and rate expressions. We're just going to use the equations to solve for times and concentrations. So let's utilize that rate law, or that integrated rate law now, to solve for one of those variables, because what these integrated rate laws come down to is just an equation where we know all of the variables except for one, so we plug them in and solve for the unknown. So the decomposition of hydrogen peroxide is first order in H2O2. The rate constant for this reaction at 20 degrees Celsius is 1.8 times 10 to the minus 5, 1 over seconds. If the starting concentration of H2O2 is 0.75, determine the concentration of H2O2 remaining after 3 hours. So let's start defining some of our variables. We have concentration of A at some later time t, concentration of A that we start with at initially, we have K, and we have T. So we know that A, the concentration of A at our later time, is going to be what we're looking for. That's what it says, determine the concentration after 3 hours. That 3 hours is our time. The problem gives us our K, our rate constant, of 1.8 times 10 to the minus 5, 1 over seconds. And we're also given the initial concentration. The starting concentration of H2O2 was 0.75 molar. Now there's one thing that we have to do before we can start plugging in our values, and that's to double check that our units are all the same. Well, we know that concentration is in molarity, so when I solve for concentration of A at our later time, that'll also be in molarity. But if we look at our K and our T, they're in different time units. So we always have to make sure that our rate constant, which is a value of time, okay, there's a time component in there, has the same units as the time, the T value in the problem. So let's convert this 3 hours to seconds. We know that in 1 hour, there are 60 minutes, and in 1 minute, there are 60 seconds. So let's grab our calculators so we can start solving this problem. So 3 hours times 60 minutes times 60 seconds is equal to 10,800 seconds. Okay, so now that our units are all the same, let's just plug everything in to our integrated rate law. So we're looking for our a sub t, which is this variable here. So it's probably easier to use the second version of this equation. Rather than the first. So we have ln of a sub t is equal to negative k 1.8 times 10 to the minus 5 1 over seconds times our t, which was 10,800 seconds, plus the natural log of our initial concentration, 0.75 molar. Now we can see that when we do this multiplication of K and T, seconds are going to cancel, leaving us only with units of molarity for our final answer, which is what we want because we're looking for a concentration. So let's simplify. We have negative 1.8 times 10 to the minus 5 multiplied by that 10,800. We're going to add to that value the natural log of 0.75. Remember, natural log is just a mathematical function on your calculator. So even though it's ln of 0.75, that's still a value, that's still a number. So we get that the natural log of a at time t is equal to negative 0.4828 molar. Now we're not done yet because that's not the concentration, that's the natural log of the concentration. So in order to get rid of a natural log, we have to take this value and do e to the, take it as an e raised to that value. That's how you undo a natural log or cancel out a natural log. So in order to do that on your own calculator, it's usually the second button and then you hit the natural log button, gives you e to the, okay? So e to the negative 0.48208, and yes, you need that negative. It will be very important, so make sure you get your sign correctly. So that concentration is now 0.61749 molar. I think we have 2 sig figs in this problem, so let's do 0.62 molar. Now, does that concentration make sense? Well, we know that in this reaction we're going from reactant to product, and we're starting with only reactant. Therefore, if we're forming product, we should see the concentration of our reactant decrease. So our initial concentration was 0.75, and our concentration at some later time is 0.62. So we're seeing a decrease in that concentration because we're creating product. And so that concentration does make sense. So always make sure to double check your answer and say, does that number make sense? If it's higher than the initial concentration, then you did something wrong. Most likely in your signs, you're forgetting a negative somewhere, or you forgot a natural log. So just keep that in mind. Let's try another one. For the decomposition of H2O2 again, this is first order in H2O2. The rate constant for this reaction is now 1.63 times 10 to the 4th, 1 over seconds. We want to know how long will it take for H2O2 concentration to fall from 0.45 molar to 0.33 molar. So here we have our starting concentrations. This would be, concentration 0, and this would be concentration at some later time. We are looking for that later time, t. So pause your video and try to solve this problem. So to start this problem, you could use either equation that was provided for the integrated rate law. So let's use the first version of the integrated rate law just to show how we can utilize that equation as well. So we have a natural log of our concentration at some later time, so that would be that 0.33, and our initial concentration of 0.45. Okay, so we have to make sure that we're putting those in the right spots. Okay, we're putting the smaller number on top and the larger number on the bottom because we're decreasing our concentration of our reactant. And that's going to be equal to negative K, which is 1.63 times 10 to the minus 4, 1 over seconds. And we're looking for value T. Now, the biggest mistake that I see students making with these types of problems is not properly typing the natural log into their calculator. Oftentimes I see students doing natural log of 0.33 and then dividing that by 0.45. That is not correct because you want to do the natural log of that ratio of numbers. So we could do this one of two ways. You could take the ratio first, 0.33, divided by 0.45, and then you can take the natural log, not the 10 log, the natural log of that number, okay? Or you could type in, and make sure you use your parentheses correctly, natural log of 0.33 divided by 0.45. Notice how I'm putting it all in that same parentheses that's with the natural log. That's telling your calculator, I want to do the natural log of both of these numbers, take the ratio of those two numbers, and then do the natural log. That's what the parentheses is telling it. So, and that gives you the value that you want. So just make sure that you are punching that into your calculator correctly. Feel free to grab your calculator and work with these problems along with me so you can double check that you're typing it into your calculator correctly, okay? Because that's always the biggest mistake I see students making, is not properly accounting for that ratio and the natural log. And that's then equal to negative 1.63 times 10 to the minus 4, 1 over seconds, times T. So now we just have to take that answer, that negative 0.31, and divide it by the rate constant, which is negative 1.63 times 10 to the minus 4. And we get a time of 1902. Now, this is in units of seconds because I have my rate constant in 1 over seconds. When I do the division, it's going to flip that seconds upside down or reverse it. So it's going to, instead of being 1 over seconds, there's going to be seconds. So this is now a time in seconds. If you were asked to convert that to hours, you can then do your conversion from seconds to hours. Along with first order reactions and their integrated rate laws, we can also discuss the half-life. The half-life of a first-order reaction, or in any reaction, is the time required for the reactant concentration to drop to half its original value. You oftentimes hear half-life equated to radioactive material because we're looking at the rate at which it's going to take for that radioactive material to decay by half. Okay, this is the same concept here. Okay, now the half-life, again, is just an equation, just like our integrated rate laws. It's just an equation that we're going to plug it into. The half-life for first-order reactions is given by this equation here. The half-life is equal to 0.693 over K. K being the rate constant. If you want to see how that is derived, I believe your textbook has a demonstration on how that's derived. You could also look that up on YouTube or on Google to find that on your own, but it is just a constant equation that we can just use and plug into. So if we know the rate constant, we can find the half-life for that reaction. So let's look at how we're going to use that. We want to calculate the half-life of the decomposition of azomethane, which has a rate constant of K equaling 2.55 times 10 to the minus 3 1/seconds. So all we have to do to solve these problems is plug in that rate constant. So 0.693, that's a constant value, divided by the K given in the problem. So 2.55 times 10 to the minus 3 1/seconds. So we take 0.693, we divide it by 2.55 times 10 to the minus 3, and we get a half-life of 271. Let's do 72 for 3 sig figs, and that's going to be in units of seconds because our K is given to us in units of seconds. Okay, so that's 272 seconds for the azomethane to decompose by half. It would take 272 seconds. Our second problem wants us to calculate the rate constant for the first order decay of sodium 24, which has a half-life of 14.7 hours. So we know in this problem the half-life, we know T1/2, and we want to use that to find K. Perfect, we can do that, we just have to plug it in. However, we know that rate constants in first order have to have units of 1/seconds. So we first have to convert that 14.7 hours to seconds so we're getting our K in its proper units. So let's take 14.7 hours. We know that in 1 hour we have 60 minutes, and in 1 minute we have 60 seconds. So we'll take that 14.7 and we'll multiply that by 60 and multiply it again by 60. So we have 52,920 seconds. It's a comma, not a decimal. Okay, so now that we have the half-life in seconds, we can plug that in. So 52,920 is equal to 0.693 over K. So K would equal 0.693 divided by 52,920. So we'll take 0.693, divide it by that answer, and we get a K value, a rate constant of 1.31 times 10 to the minus 5 1/seconds. So for half-life in those integrated rate laws, that's all we need to know for our first order reactions. But we can apply the same concept now to a second order reaction in order to find the second order integrated rate law. Now I'm not going to show any of the derivations or anything like that because for second order it's very similar to what we do in first order, and your textbook does a really great job of showing that if you're really interested. But again, these reaction integrated rate laws and these half-lives, they really just come down to equations that we need to know and utilize to find our values. So a second order reaction is a reaction whose rate depends on the concentration of one reactant raised to the second power, or on the product of two concentrations of two different reactants, first order in each. So the second order integrated rate law is given here. 1/AT equals KT plus 1/A0. And the second order half-life is the half-life is equal to 1/K times the concentration, initial concentration. So now we no longer have those natural logs in there. But again, these are just the two equations that we're going to utilize for the integrated rate law and the half-life. And as long as we know our values, we can solve for our unknowns. So let's jump into practicing that. For the following reaction at a certain temperature, it has the rate law. Rate is equal to 0.0186 times the concentration of NH3 squared. Suppose a vessel contains NH3 at a concentration of 0.570. Calculate the concentration of NH3 in the vessel at 460 seconds. And then I also want to add on here, let's solve for the half-life. Let's just do both since we have the equations for both. So to solve for the, let's see, we're looking for the concentration after 460 seconds. So we're looking for concentration at some later time t. We know our initial concentration of NH3 is 0.570. We know K, that's given in the rate law here. So we know that K is 0.0186, 1 over molar seconds. And we know T is 460 seconds. So now we can just start plugging things into both equations. Let's do our integrated rate law first. So we take 1 over the concentration of A at some later time T. That's what we're solving for. We're going to take K, which was 0.0186, multiply that by the time, 460, and add to that 1 over the initial concentration, 0.570. So let's simplify. 0.0186 times 460, add to that 1 divided by 0.570. And we get that the 1 over the concentration at some later time is equal to 10.31. And that's 1 over molar. Now we're not done yet because that's not the concentration, that's the inverse of the concentration. So you could invert this one of two ways. You could do 1 divided by 10.31, or you could just raise this to the -1 power. I like raising it to the -1 power because it's just a button on my calculator, like I just showed. But however way you see inverting, go for it. So that gives us a concentration at our later time of 0.09698. Let's see, this one says 2 significant figures, so that would be 0.097 molar. And again, we can use our concept of does that concentration make sense? We know that our concentration at a later time is always going to be smaller than the initial concentration. So the initial concentration is 0.570 and the final concentration is 0.097, which is smaller than the initial concentration. If you forgot to invert and you put this as your answer, you can also stop and think, does that make sense? Would it make sense that my concentration went from 0.57 all the way up to 10.3? No, that wouldn't make sense if I'm using up my reactant of NH3, therefore decreasing its concentration. So always use your kind of number sense that goes on in your head. Always use that to just double check your answers. Now let's find the half-life. Even though the problem didn't ask for it, let's just do it anyways, since we have the equation. So our half-life, T half-life, is equal to 1 over K, 0.0186, times the initial concentration, 0.570. So let's do that on our calculator. 1 over, I'm going to utilize my parentheses, 0.0186 times 0.570. And we get a half-life of 94 seconds. Again, that K has units of 1 over seconds. Well, actually, it's 1 over molar seconds. And then when we multiply it by that concentration, the molars end up canceling, and we get 1 over seconds seconds as a half-life because we're doing the inverse. So half-life should always have units of seconds. Okay, and then we have zero-order reactions. Now, zero-order reactions just come down to, again, a constant. Okay, the rate is really not dependent on any of the concentrations of the reactants or anything like that. So we can, again, just look at their integrated rate law and the half-life as equations. And then there are third order and higher reactions that have integrated rate laws and half-life, but they're rare in what we would see in general chemistry 2 and also very tricky to derive. So we're just not going to focus on those. We're just going to look at 0, first, and second. So this chart here tells us our reaction order, our rate law, our integrated rate law, and our half-life. You are going to be given this on your exams. This exact table will be given to you. Okay, so just make sure you know how to use it and how to plug everything in and solve for what the value that you need. So for 0 order, which is the new one that we're looking at, the integrated rate law is very similar to the second order rate law, where we have A at some later time is equal to negative kT plus the initial concentration, and the half-life is dependent on the concentration over 2 times K. So let's utilize those two new equations and practice some 0 order reactions. So under certain conditions, the rate of this reaction is 0 order in dinitrogen monoxide, with a rate constant of 0.0057. Suppose a 35 milliliter flask is charged under these conditions with 350 millimoles of dinitrogen monoxide. How much is left after 40 seconds? You may assume no other option. So let's solve for our concentration, but since we have the information and the equation, let's also solve for our half-life. So this problem, we don't have any concentrations yet, but what we do have is a volume and a mole value. And we know that if we have moles and volume, we can do moles per liter, and that is equal to a concentration. Okay, so we have to recall our memory of General Chemistry 1 when we learned about molarity and concentrations. So we're going to do moles over liters, so that would be 0.350 moles. For some reason, Alex likes to give millimoles sometimes. So just make sure that you're converting those. It's not a typo that there's 2 M's, it actually is millimoles. So just make sure you're converting those using the 1,000, just like you would milliliters. So we get 350 millimoles is 0.350 moles, and 350 milliliters is 0.350 liters. So that's a concentration of 1.0 molar, right? 0.35 divided by 0.35 is 1. So that's our initial concentration. Okay, so now that we've solved for the initial concentration, what I want you to do is pause your video and try solving for this problem using your rate law, integrated rate law, and your half-life. So find the concentration after 40 seconds and then find the half-life. Even though the problem doesn't ask for it, I'm asking for it. So solve for the half-life as well. Let's plug everything in. So we're looking for our concentration at some later time t. We know that the rate constant is 0.0057, and that time that we're looking at is 40 seconds. We're going to add to that our initial concentration, which we found was 1 molar. So we'll plug that in, negative 0.0057 times 40. We'll add to that 1.0. And we get a concentration at our later time of 0.772 molar, which makes sense because we decreased from 1.00 molar. So that's 0.772 molar. And to solve for the half-life, T1 half is equal to that initial concentration of 1 molar divided by 2 times that rate constant, 0.0057. So 1 divided by 2 times 0.0057. So the half-life is equal to 87.7 seconds. Again, half-life has units of seconds. Okay, so now go to your ALEKS homework and practice utilizing these integrated rate laws and the chart of equations, making sure you know which one to utilize and when, and practice more there.